Hey everybody, so welcome to a little mini lecture where we're just gonna go over 1.4, which is not very long. So let's get started. Okay, and it's freezing in my house, which is why I'm all bundled. Okay, all right, so we're gonna talk about, so this is section 1.4, hold on. We're gonna talk about section 1.4, which is all about heat and work. And we're gonna put some definitions down so that we can understand this better, because it's a big part of the course. Heat for sure, work for sure. So we've got to really have an understanding. Before we do that, let's set down the two first laws that you are going to see in thermodynamics. Now I'm going to move my picture because I keep looking over at the side. Okay. All right, there we go. That'll work a little better. Okay, so let's take a look at two laws. Now, we're going to start with the 0th law of thermodynamics. And so I'll put this in a different color. Okay, so 0th law of thermodynamics. Okay, what does that tell us? So that tells us very simply that if you take a hot object and put it next to a cold one or a cooler one, cooler object, heat will flow from the hot object to the colder one. Pretty intuitive because we deal with this every day, right? One of the reasons I'm bundled up right now is heat is flowing out from me out into my room, which is colder. Okay. And from the, I should say from the hot object to the cooler one or a cold one in a well-defined way. Now, we're not going to really understand that until later, what well-defined means, but we're just stating the law. Okay. Again, this allows us to define temperature, right? Otherwise, we really couldn't. No, this is the fact. This is the case, right? Okay. So let's write down the first law. So these are the first two laws that we're writing down. Get a whole different color for that one. Oh. All right, so then we have the first law. And that states, it really is, people like to think of this as it says you can break even. Okay, what does that mean? It means that if you're clever enough, so if you are clever enough, right, you can figure out that's not a Q, G. Figure out how to, say, run your car using the heat in the air, let's say. Okay, this is really kind of a statement about how you can use heat to do something like make a car go. Okay, and it says this is possible, like physically possible to do. Now, we are not clever enough, and the first law is superseded by other laws that make this not exactly true, but we're starting from there. Okay. So the first law is really telling you about heat and work, okay? Remember from physics, work is a quantity that is related to a change in the in an object's kinetic energy, right? It's something that is only defined as a change. You can't, there's no such thing as the amount of work in an object, right? There's the amount of work that it's always with relation to something else, into to relation to some level. And we'll see how that works more. Okay, so what are heat and work? And this is where we can write down actual definitions of heat and work. So for heat, what is it? Okay, very specific definition. It is the spontaneous flow of energy from one object to another, caused by a difference in temperature between the two. By the way, when you watch these videos, I just want to point out to you that if I'm going too slow for you, you can always watch them at higher speed. If I'm going too fast for you, you can watch them at lower speed. I don't know if you've ever done that on YouTube videos, but they allow that, and you know, speeding up or slowing down doesn't change the pitch of my voice or anything. Just slows down the video. Okay. All right. Okay. What about work? Okay, work is literally any other transfer of energy in or out of the system. Any other transfer of energy. So we're making a broad definition of work. Okay, all right. So this is a good point to, a good place to actually do some examples to try to figure out how do we use this to say what something's heat or something's work. And it's very important to be able to tell the difference between these two things. So I'm actually going to get another layer on here. So, and I'll kill this one for now, but we're gonna make a table. Okay, all right, so let's do a table. So we're gonna write down something like, well, you'll see, situation, for instance, rubbing your hands together. And I'm going to call this the events. And then I'm going to say, is it heat? Is it work? Or, and is there a change in temperature due to this? And what is the system? Because we said something about heat flowing into a system. We said also, right, any other flow of energy in the system. And it would be nice to just define that for these terms. I mean, for these events, because they can get confusing. So let's just write the column here. Okay. All right, so rubbing your hands together, it kind of seems like it should be heat, right? But think about it, right? You have a change in temperature, right? And the system is your hand. So what's happening is there, well, actually, why don't we, let's go back and read our definition real quick. Wish I could have both on the same screen. Spontaneous flow of energy from one object to another caused by a difference in temperature between the two. Okay. So one hand is not hotter than the other, right? And one hand is not giving heat to the other, right? So this must be work, okay? Because your hands do get hotter. All right, so let's see. So this must be work. So this is work. And oh, that's supposed to be purple. Well, pink, purple. And the delta T definitely goes up, right? And the system is the hands. Just want to make sure I've got everything right here. Let's go back to the orange. Okay, what about a cup of tea? Sorry for the wrong color there. A cup of tea warming in microwave. Okay. Let's just do a couple more of these so I don't have to keep going back to that color. Okay. All right. Now, obviously, the tea is getting warmer. But what is happening? Is there energy transfer from a hotter object to a cooler object? No. The microwave isn't hot inside like an oven would be, right? What's happening is the microwaves themselves are making molecules, changing the kinetic energy of the molecules, right? So this is not heat. Heat is not spontaneously flowing into your tea, okay? It's work being done on the molecules themselves by the microwave radiation that comes into your, which is basically light, right? Microwaves are a form of light. So it is not heat transfer, right? You certainly get a change in temperature, and the system is the tea, right? Okay. All right, because where energy is flowing, work energy is being transferred to the tea. Okay. All right, what about this situation where we have a little battery? Plus minus terminals on the battery. And then we have a little cup over here. Okay, little cup. And in what we do is we hook up some wires to this, and we put it in the cup. And then we have a little coil, and then we come out of the cup and hook here so that you have current flowing through this little coil, right? Which should make it hotter, the coil, okay? And so what is this? Is this heat or work? Okay. Well, the flow of energy from the battery to the resistor. So think of this little coil thing as it's just a resistor. Okay, kind of like in the regular old light bulbs where you pump current through and they get so hot that they glow. So there's two things going on here. There's energy flowing from the battery, so this is the battery, to the wires in the resistor, right? That is not heat. Energy is transferred, yes, from the battery. If you keep running it, the battery is going to run out of energy, right? So there's work there. So there's two things here, okay? So I have to make a little half line here in orange to specify the two things that are happening, okay? Let's see. I can leave that one. All right, so let's see. Here we go. So we have energy flow energy from battery to the resistor. That is definitely work, not heat, right? Okay, but that resistor is heating up. And the reason your tea is going to get warm is that the energy, the heat is going to be transferred from the hotter thing, the resistor, to the colder thing, the water, right? So energy from R to water. This is battery to R, right? To R, sorry, there's like no room there. That is heat, okay? And of course, the system is the water with the T, right? So that's what we're talking about here, okay? But there's two systems here, right? There's the system, I guess there's two systems, so I should be a little more careful. Two systems here, because one of them, we talked about energy flow from the battery to the resistor, right? In that case, it's the resistor. And okay, so there is a change in temperature, goes up. And then the system is the resistor. And then on this one, right, there is a rise in temperature and the system is the T. Okay? All right. Hope you can start to see the differences here. Okay, what about keeping water boiling on a stove? So you bring your pot up to boil and you just let it, if you're cooking pasta or something, right? You would just leave it on so that it would keep boiling. So your pasta would get cooked, right? Okay, so what's happening? Okay, well, there's no temperature rise, right? But definitely you could probably think of a flame underneath the pot is transferring heat from the hot flame to the water, also the pan, but right, never mind that, right? But it's going to the water and keeping it boiling. Now, heat is definitely flowing in, right? To keep it boiling, but there is no change in temperature because water boils at 100 degrees centigrade and that's that, right? Celsius. So no change in temperature. It's definitely heat. My color scheme's off here. And the system is, of course, the water. Okay. What about, let's go to the next system is, what about let a piston out? Let's have a little cylinder. It has a little piston here. Okay. And there's the top of the piston here. So what if we let the piston out fast enough for the gas to cool? So we just sort of let it go and it'll push its way out and the gas cools down. Okay. And we have to heat up the gas. So let's heat it up first. So we have one phase here where we're heating the gas, and that's pretty obviously heat. It's kind of like that, that keep water boiling. So if we let the gas cool by letting the piston go out, sorry, that looks like a very different cylinder, but it's supposed to be the same one. So we let the piston go out fast enough to cool the gas, right? What's happening is the gas is cooling, and it's cooling because it's transferring energy out, heat. So this is definitely heat being transferred, okay? And the system is, the delta T is down and the system is the gas, okay? Okay, so I hope that gives you a little intro into the differences between heat and work. So just remember that heat is this sort of spontaneous transfer from hotter object to a cooler object, right? And everything else we call work, every other thing, right? The microwave making the molecules go back and forth and creating more kinetic energy, which means hotter temperatures, that's work, right? Not heat. Okay. All right, so let's look at just talking about the total change in thermal energy, okay? If we look at the total change in thermal energy, it will be equal to, right, any heat that flowed into the system or flowed out. So this really is delta Q, change in heat, but we don't always have to write the deltas. In fact, you'll probably see in your book, they don't even write the delta here, right? It's just U, okay? Plus any work that was done on the system or by the system. And we're gonna make that distinction between working on the system and work by the system on the environment very clear and distinct. But these are both deltas, even though we don't write delta. So the total change in energy is going to be the heat that flows in or out, plus the work that's done on the system or done by the system, right? Okay. So that is basically all we have to do in this little tiny section. So hopefully you'll be good to answer the question that is on the homework for Thursday. Okay, talk to you soon. One second, it won't turn off.